So you should know now that convolutions are a good technique to actually reduce the computational complexity of neural networks by quite a lot without really losing any accuracy. We can make programs manageable that aren't really manageable with traditional neural networks that are fully connected, connecting everything to everything. Now, there is another advantage of convolutions, and it's coming from other disciplines. So what we haven't discussed yet is that convolutions can be also used to implement priors of the data. So what we would usually do is we would have our image, for example, or any other spatial input. And for a traditional neural network, what we would need to do is to flatten that image into a one-dimensional vector, right? For example, a 32 by 32 by 3 channels RGB image would be flattened into a 3072 by 1 vector, which is then processed by our either traditional or convolutional neural network. Now this has an inherent problem because it does not sustain any spatial structure. It doesn't preserve any spatial structures in the data. Just imagine if I move that whole image a little bit to the right or to the left, the whole structure of that image and the neighborhoods in that vector, in that one-dimensional vector, would completely change. Now, in the traditional network, I would just apply my weight matrix, of course, and then every single one of my output elements, in this case, it's 10 output elements, probably 10 classes in a CIFAR 10 dataset. It's just a multiplication of my input data with my weight matrix entry, and then probably followed by an activation function. We'll talk about activations in a future video. However, we can preserve more information and keep and leverage convolutions to their maximum potential for preserving structure, for example. And the idea is very, very simple. If I keep my image as it is, say here we have our 32 by 32 input image and three channels. It's just the color channels, RB, RG, and B. So we can convolve this with a filter that has also a spatial structure. So say, for example, a 5 by 5 by 3 convolution filter. It's the same principle, can connect 5 by 5 by 3 elements to this filter and then evaluate the output as I would do in my one-dimensional neural network. Now, this idea is well known for those of you who visited the computer vision courses. You're very familiar probably with image edge detection filters, smoothing filters, sharpening filters, for example. If you just implement filters like this and apply them the same weights, just on different locations in the input image, if you define your filter kernel like this, then you'll get edge detector, for example. If you define it like this, then you have a sharpening filter preserving local details. If you define it like this, you get a Gaussian blur function. But remember, these don't have to be fixed. We can actually make all of these learnable, randomly initialized and then learn through backpropagation. And we can learn really a lot of these filters, all of them extracting a specific detail of our images. Now, convolution of a filter kernel with an image is something you're probably familiar with. It's just a dot product between the two at different locations in the input image. So, and the dot product in this case is really loosely defined. It really means just multiply each element with each element and sum up. That's it. And so you can basically use any shape here that fits a dot product. The output will be one value. Right? This is one value in one feature map. And this filter can then be applied like a sliding window across the whole image, just at different locations, so that we get an output image with lots of these individual locations, a bit smaller than the input image. Now, if you look closely, if you run this filter now over the input image, what will happen is that I have to consider some boundary region here for my filter. So the output, if this input is 32 by 32, the output will in this case be for a 5 by 5 filter be 28 by 28. Right? It eats off 4 pixels of each side because it needs it as input to build this dot product. The obvious solution to this, if you don't want that your input shrinks over time, is that you zero pad your input. So you add zeros at the boundaries. You add as many zeros at the boundaries as you expect shrinkage in your output. So if I add 4 zeros here, I have an input image of 36 by 36 where the yellow regions are just zeros, then slide over all locations, my output will again be 32 by 32 by 1 in this case. So all the 3 channels at a 5 by 5 by 3 filter will collapse to 1 single value. And we call this output here 1 feature map. So I can learn a lot of these filters. I can just define a whole filter bank for my input or learn through backpropagation. And each of these filters is individually applied. So they are during inference constant rates just applied at different locations. And each of these filters will produce 1 output map. So it could be that I can define convolutional network, which has a 32 by 32 by 3 input image. And in most tensor processing frameworks, I would call this from here on now input tensor of size 32 by 32 by 3. We're producing, by learning, 6 5 by 5 by 3 filters, 6 feature maps. So basically an output tensor of size 32 by 32 by 6. Right? Each of these layers of my output tensor here is 1 feature map learned from 1 filter. But overall, the filters are small. So this is all the parameters I need to learn to get to such a representation of my input data. So a CNN now, a convolutional neural network, is just a sequence of convolutional layers which I can interleave with activation functions. Like very common, for example, is the ReLU. We will talk about activations functions in a separate video, but the CNN itself is nothing else, just assembling these filter layers and the feature map outputs interleaved by activation layers. So I can stack up as many as I like and play around with the tensor sizes that come in and come out until I get to my desired result. For example, a small representation which is good enough to be fed into, for example, a traditional neural network. 64 by 64 by 1 output tensor would be well suited, for example, for a fully connected layer to make some classification results, for example. So all this is a really, really good feature extractor that can be tailored and trained towards the task at the end. Now let's look at the complexity of these networks in a little bit more detail. So in this particular example where we filter with a 5 by 5 by 3 filter, we need to add 1 because we can't forget the bias, of course, in a neural network. So each filter has 5 by 5 by 3 plus 1 parameters, so 76 parameters. And 76 by 6 filters, the whole filter bank has 76 parameters times 6 filters is 556 parameters for this layer here. In this layer, we're convolving with 3 by 3 by 6. So this convolves now the entire feature map here, plus 1 for the bias. Don't forget the bias. Equals 55 per filter, 55 parameters per filter. So 55 times, say, 10 filters here in this case, that I get a 10-dimensional feature map, is 550 parameters. Okay? Now what I can also do, which is quite interesting, is I can do a 1-by-1 convolution. So basically multiply each input element individually with, here in this case, 1 by 1 by 3 filter. So I can reduce the dimension, the channels from 3 to 1 here by this operation, and I basically I can use this to build linear combinations. It's actually exactly the same as building combinations that can be mathematically proven, but the advantage of doing something like that is really that you can formulate your entire network only with convolutional operations without needing to integrate other formulations of combinations. Now, one thing we need to take care of is padding and strides. I briefly mentioned that you can pad your input to be in control of the output side. What you have also control of is the stride of your sliding window. So by how many pixels you move the filter from step to step. So I can, for example, move a 7x7 input. At this 7x7 input, I can move a 3x3 filter over this input with stride 1 and no padding. And now think about it, what the output will be, the output size. I'm losing how many? I'm losing 1 per side, right? So I have a 5x5 output. Now what I can do is I can have the same operation, but if a stride of 2, so I move by 2 pixels for every step here with no padding, will produce a 3x3 output, right? So I can reduce the output size by quite a bit by jumping over a few pixels while not losing too much information, because the information will still be in the convolution neighborhood of that filter kernel. Right. So with zero padding, I can get to other output sizes. So the computational complexity in general for this network is if I have a 5x5 kernel here, and this is just for illustration reasons, and I have an n by m by d channels input, then I will get an n minus 4, so filter kernel size minus 1 size. So this filter kernel will eat off 2 pixels on each side here, right? So each side is 2 by 2 is 4. So the size will be reduced by 4 here on each side. Number of channels in this case is only affected by the number of channels of the filter kernel. So each position consists of 5 by 5 by d multiplications times n minus 4 times n minus 4 positions times the number of filters d. Now, if we talk about complexity, we only look at the multiplications because the additions and subtractions can usually be done in one clock cycle on modern hardware. So the only interesting part here are really the multiplications if you look at that. So we have in this overall setup 25 times d squared times n minus 4 times m minus 4 operations. Now in our concrete example, so the 32 by 32 by 3 image, that would mean 176,000 operations. Now, as an exercise, you can try and calculate how many operations it would take to do this with a fully connected network and how much more that really is. You can probably even estimate from the previous slides where we said that a fully connected network needs n squared parameters. So from that you can probably estimate what's the difference of the magnitude of the two complexities of a convolutional neural network with filter kernels and spatial preservation of structure to a linear fully connected network. Anyway, I can even go further and do something interesting. If I just look at the output sizes, I can get the same effect by stacking up smaller filters on top of each other. So I can get from n to n by m by d to n minus 4 by m minus 4 by d with 2 3 by 3 filter operations followed by each other. So that's That probably is not entirely the same. It's an approximation of the 5 by 5 by 3 filter. The 5 by 5 by 3 filter has obviously can produce more combinations than the 3 by 3 and the 3 by 3 filter. But it's a really good approximation, and this is actually used a lot to approximate very large filters if they are required. If you look in detail here, the 3 by 3, of course, is just one pixel off the side of each side of this of the input. Then I end up with n-2 and m-2. Then I eat another pixel off of each side, so I end up with n-4 to m-4. Complexity in this case is 9d squared n-2 times m-2, and the same here with n-4 times m-4, because 3 by 3 is 9, right? So in our concrete case, this is just 160,000 operations. So I saved a quarter by just doing this. I made it faster. In the extreme case, I can use separable convolutions and really just do, for example, a 5 by 1 convolution in one direction and then followed by a 5 by 1 convolution in the other direction. You might be familiar with this concept from computer vision as separable filters. They are massively more efficient, especially when it comes to very large filter kernels. So in this case, the complexity for our 32 by 32 by 3 network is just 73,000 operations. So we have saved probably 2/3 of the operations by just doing this and made it massively faster. This can be quite important if you have really strict real-time requirements for your inference paths. And it also makes training faster because of course, training always involves at least one forward pass to get to the error for backpropagation. So this can be important and is used a lot, but on the practical side, it's also not quite common, at least right now, to use very large filter kernels. In the early convolutional neural network works, it was quite common to use larger filter sizes, but it has been shown in several works that it's actually good enough to use smaller filter kernels to achieve pretty much the same effects. Smaller filter kernels, deeper networks get to even better results than having large filter sizes and shallower networks. Now, one additional thing we do in CNNs is pooling, and pooling basically is a permutation, invariant, aggregation, and downsampling. And very typically we use max pooling, sometimes average pooling. Max pooling is the more common one, and the only purpose for it is to A, introduce some local shift invariance, and B, to reduce the dimensionality of my input size. So it works, it's very simple. The only thing it is really, I look at blocks of my input size and then take the max or the average. So if I look at this block here, for example, the maximum is 6, so I keep this maximum and enter 6 in my downsampled output of this operation. Here, the maximum is obviously 8. The maximum here is 5, and the maximum here is 4. So this is the pooling output. So interestingly, it has been shown that at least for certain benchmarks, you don't necessarily need pooling. You can achieve the same effect with convolutions, and really, if you build carefully deep networks that reduce naturally your input size through convolutions, through eating up pixels around your input image, then you can achieve a similar effect than is achieved by pooling. So it's not absolutely required, but it's very common in networks to just go quickly down in the dimensionality through a not too deep network. And yeah, pooling is usually applied to each channel separately, so you wouldn't apply pooling across channels, you just do it per channel layer in your feature map. Now, what do CNNs learn? And this is a very interesting question. It's an own field of research, how to interpret what neural networks memorize and what they actually learn about the world. And well, there's one way you can probably look at this is to visualize the feature maps directly, what comes out, and accumulate them. Probably put them in a color map, so the representation is relatively hard if you have a, say, 100-dimensional filter output with 100 filters, but you can map them on a color scale at least. So what you see is that in the shallower layers, some very basic filters are learned. Looks sometimes a little bit like filter banks from computer vision, and it's more focused on textures. While in the higher layers, like layer 3 here, it looks like more detailed textures and more abstract objects are learned, like here faces, or here these particular patterns. If you go much deeper, then it's apparently becoming more abstract, like the representation of these bowls or legs, which are highlighted here. But it's really difficult to tell. Or in the even deeper layer here, eyes, the concept of an eye, apparently this filter reacts very strongly to eyes, this one very strongly to wheels, and I'm not so sure about this one. This one apparently likes ears and activates strongly for ears. But this is very hard, and this can be a problem. For example, in medicine, where I'm particularly interested in fully understanding what my algorithm does, because I need to be fully aware of all error sources, not only because of regulatory requirements, but perhaps as a patient, I want to know why a computer says yes or no to a certain treatment, right? And this is very difficult in convolutional neural networks, and still a very, very active topic of research. As I said in the beginning, I'll spare you all of the details of the history, but really convolutional neural networks as we know them are not really a new invention. Kind of the community agrees that the first idea in this direction was probably proposed by Fukushima in 1980. He used ReLUs and everything which are currently used. The only problem with his approach was that he didn't have backpropagation to train his approach to new data. So it wasn't really a useful algorithm. It was more like an idea. So you can think of it what you like, but probably that was the first convolutional neural network focusing on local feature similarity. Then probably the first one who made it work was LeCun in the 90s, because he and the Hinton lab and so on added backpropagation to training of these networks, and these networks had surprisingly large filter kernels, actually, so 14 by 14, 28 by 28 filter kernels, which is not so common anymore, but it worked really, really well for the character recognition in images, which he did. And it was still slow to train and only worked on really, really small input. That's where this 32 by 32 image input size comes from. Really, the hype was probably triggered by the implementation of these approaches on GPUs, which made it just feasible to train larger and larger training databases quite quickly. Because if you think what's actually required, the filter times image dot product, that's just a matrix vector operation, and GPUs are really, really good in doing relatively dumb matrix vector multiplications, and you can speed it up quite a lot with GPUs, and probably that really triggered the deep learning revolution in combination with the previous works. There is in the computer vision community, there is a challenge called the ImageNet challenge. It's just a number of small images, millions of small images, which have been labeled what it contains: a dog, car, truck, and so on. And this has been around for a while, and the previous best approach before the deep learning revolution had some error of 26% for this task. And the first done by Alex Krzyzewski was AlexNet in 2012, which beat the previous state-of-the-art approach by quite a large margin, so something around 10%. And seems like this was quite reliable improvement until a few years ago, when people discovered that these networks become actually better than a human doing the same task, so doing a classification task on that. And not only one, they tested actually quite a lot of humans. There are some debates in the community if this is probably now overfitting to the test data set, but that's probably for everybody on their own to decide what's the actual problem here. Maybe the AI outperforms humans really, or we just overfit to all of the test images that are available in this data set. But most of this was initially proposed in the 1980s and the 1990s. The difference is it works now. So what do we learn from this? Well, already last time we learned that convolutions can massively reduce the computational complexity of neural networks, but the real power of CNNs is revealed when priors are implemented. And for example, spatial structures are preserved. This is also one of the reasons why CNNs have been so successful in the computer vision community. So CNNs themselves are nothing else than a pipeline of learnable filters interleaved with nonlinear activation functions, producing d-dimensional feature maps at every stage. Training works like a common neural network. You initialize your weights randomly, you present examples from the training database, make a forward pass, then compare whatever error you produce at the end, and propagate this error back with back propagation to the network to update the individual weights. Really the same thing as a traditional neural network. And C, convolution and pooling can be used to reduce the dimensionality of the input data until it forms a small enough space for either traditional machine learning methods to do things like classification, regression, or similar, or perhaps to steer other networks to, for example, generate a semantic interpretation, like, for example, a mask that fits the input image and that masks out a particular object of that image.